Hello everybody. Today I'll be talking about MIMO system with Alamouti Space-Time Block Coding scheme. The key topics studied in this project are as follows. Firstly, we have system classification and MIMO systems, then singular value decomposition or SVD, water filling algorithm, Alamouti STBC for 1x2 system, Alamouti STBC for 2x2 system, simulation results, observations and conclusion from simulation results. Now to start with, we know that there are a number of systems in the field of electronic communications that are classified based on the number of transmitting and receiving antennas. MIMO, that stands for multiple input, multiple output, is that kind of a system that has a number of transmitting and receiving antennas. Likewise, there are other systems like SIMO, MISO, and CISO, where S stands for single, M for multiple, I and O for input transmitting antenna and output receiving antenna, respectively. These are illustrated in the diagram here. Next, we come to the modeling of a MIMO system. Let us consider a MIMO system having T transmitting antennas and R receiving antennas. Then the modeling of the MIMO system will be as given in the equations here. It is assumed that Y1, Y2 up to YR are multiple received signals to receiving antennas, X1, X2 up to XT are the multiple transmitted signals to the transmitting antennas, N1, N2 up to NR are the multiple noise signals at the receiving antennas, H11, H21, etc. up to HRT is the H matrix or the channel matrix that characterizes the MIMO channel. MIMO concepts are based on three main factors, namely pre-coding, that is concerned with the creation of beam formation in more than one stream. It is also known for reduction of the multipath fading. Beam formation will be explained in the later slides. Secondly, we have spatial multiplexing that refers to the various streams of data being transmitted from different transmitting antenna to the receivers at the same time. Finally, we have diversity coding, which implements the space-time coding to transmit data effectively when we are unsure if a proper channel exists at the transmitting end or not. Another important concept in MIMO is the singular value decomposition or the SVD. Here, the channel matrix decomposition is done to obtain singular values, and this leads to the MIMO channel logical beam formation. Considering an equal number of transmitters and receivers, in that case, the singular value decomposition of the channel matrix is given by U sigma V Hermitian. In the second equation, sigma 1, sigma 2 up to sigma t are the singular values. Next, we come to the conditions for the singular value decomposition. Firstly, U of I modulus square should be unity. Secondly, U of I Hermitian into U of j should be equal to 0 provided I is not equal to j. The same conditions are true for V as well. Now U and V should be unit matrices. Sigma 1, sigma 2 up to sigma t are known as the singular values and they must be ordered and positive. That is, sigma 1 to sigma t must be arranged in decreasing orders of magnitude. If all the above conditions are taken care of, then we have the decomposition value of the channel matrix as H bar equal to U sigma V Hermitian. After the singular value decomposition, we have the model of our entire system that is shown in equation 1. Here, y1 tilde, y2 tilde up to yt tilde are the received symbols at the receiving end. x1 tilde, x2 tilde up to xt tilde are the transmitting symbols at the transmitting end. We find that y1 tilde depends on x1 tilde and n1 tilde. y2 tilde depends on x2 tilde and n2 tilde, and this goes on up to the tth term. This means that the receiver receives the symbols from the corresponding transmitter only. For example, if the first receiver receives the symbol, it is only from the first transmitter. The same is for all the transmitters and receivers. This particular phenomenon is known as the logical beam formation that takes place at the precoding stage of the entire system. This also means that spatial multiplexing is taking place. Another important point to consider in the system is that of power allocation in a channel. The total channel capacity is given by summation from I equal to 1 to t log to the base 2 1 plus pi into sigma I square divided by sigma n square, where sigma n is the noise power, sigma I is the singular value of the ith channel in the channel matrix, and pi is the power of the ith channel in the channel matrix. Next, we have to detect the optimal power allocated to all the participating channels we have found out by Lagrange's multiplier method. We also use the water filling algorithm that says that any value of the channel power exceeding the threshold of 1 by lambda, where lambda is the Lagrange's multiplier, is considered to be 0, and any channel having power less than the threshold will have optimally allocated power. Now we come over to Alamouti Space-Time Block Coding for 1x2 system. It was first proposed by Siavash Alamouti in the 1x2 system. We have two transmitting antennas sending symbols to a single receiving antenna. Moving on to the mathematics involved in the Alamouti STBC 1x2 system. First, we have two transmitting antennas that send two symbols to the receiving antenna at two different time instants. In the first time instant, the symbol y1 is received and is equal to the product of the channel matrix and the transmitting symbols, which is further added to the noise at the receiver end. In the second time instant, the symbol y2 is received, assuming that the channel matrix hasn't changed at all, and is equal to the product of the channel matrix with the transmitted symbols of the Alamouti schemes. This is again added to the noise. The transmitting symbols of the Alamouti scheme are shown in the equation beginning with y2. So the entire 1x2 system using the Alamouti STBC is modeled as shown, where the symbols have their usual meanings, and this modeling is done for two different time instants. Now W1 and W2 are the beamformers. These are required for decoding the transmitting symbols of x1 and x2 respectively. Their values are also shown in this slide. In order to decode the symbol for transmission at time instant 1, we multiply W1 Hermitian with y bar, and after simplification we get it equal to h double bar into x1 plus n tilde. This implies that in the first time instant, the received symbol is decoded and it depends on the symbol transmitted from transmitter 1. Similarly, for the second time instant, the received symbol would be dependent entirely on the symbol transmitted from transmitter 2. The value of h double bar is also given. Coming over to Alamouti STBC for 2x2 system. Here Alamouti scheme has been applied to two transmitters and two receiver systems. In the transmit instant 1, y11 and y21 are received at the receiver 1 and receiver 2 respectively. x1 and x2 are the transmitted symbols from transmitter 1 and 2 respectively. These are multiplied with the channel matrix. N11 and N21 are the noise powers at receivers 1 and 2 respectively at time instant 1. Similarly, we have the second equation for the received symbols at the second time instant. The only difference is that the transmitted symbols here are minus x2 conjugate and x1 conjugate because of the Alamouti STBC application. Now, after some rearrangement and modification, the entire system can be modeled as shown in the equation. The value of the channel matrix H is also provided here. Now we come over to the simulations. Both the Alamouti STBC 1x2 and 2x2 systems were introduced to a Rayleigh fading channel using the binary phase shift keying modulation technique. We started with the measurement of the bit error rate or BER of different theories like AWGN theory, the Rayleigh theory, and the Rayleigh simulation theory. Now on simulating the Alamouti 1x2 system and comparing with the MRC scheme with one transmitting antenna and two receiving antennas, we found that the bit error performance of the Alamouti scheme, although better than our classical one transmit and two receive antenna, was actually roughly 3 dB poorer than the MRC one transmit and two receive antenna. So we can conclude that the Alamouti 1x2 system is not as good as the MRC 1x2 system in this case. Moving over to the simulation results of the Alamouti 2x2 system, we can see a remarkable increase in the bit error performance of this system as compared to the previous MRC 1x2 system. So we can clearly observe the following. Firstly, the Alamouti STBC with 1x2 system performance is about 3 dB poorer as compared to the MRC 1x2 system. However, when Alamouti STBC with 2x2 system was used, it showed remarkably better performance than that of the MRC 1x2 system. So the Alamouti STBC with 2x2 system is much better than the Alamouti 1x2 system. It has also been observed that the diversity order of Alamouti STBC with 2 transmitting and R receiving antennas is 2R. And also, in both the Alamouti STBC 1x2 and 2x2 systems, there are no crosstalk errors. The noise in both cases is basically white noise. To conclude, it can be said that in the MIMO systems, several factors like pre-coding, spatial multiplexing, diversity coding, singular value decomposition, and water filling algorithm have contributed to the increase in the data rate, reduction in the transmission error, and optimization of power without increasing the bandwidth. Secondly, the BER performance of the Alamouti STBC in the 2x2 system is much better than that of Alamouti STBC in the 1x2 system as well as in the MRC 1x2 system. Here we have the section of references. Finally, I would like to thank our professor, Dr. Wu, without whom it would have been difficult to understand many concepts in the wireless communication course. We owe him for inspiring us always and making it possible for me to do this project successfully. Thank you very much for watching this video.